So this lecture is the second lecture on the limitations and extensions of PINNs. So we talked a lot about some of the limitations and extensions last lecture, and so this is going to continue that discussion. So let's just recap a couple of things from the last lecture, and this is the key slide showing you kind of the main advantages and main limitations of at least standard physics-informed neural networks. We're focusing on these two lectures on these limitations. And so I described these last lecture. The big kind of three limitations that we typically see is that PINNs are often computation expensive to train, especially when you only want to solve the kind of forward simulation task with PINNs. They can also be very hard to optimize. It's not obvious or trivial whether the gradient descent or whatever optimization algorithm you're using will converge to the kind of global minima of the loss function. And often that's not the case. And coupled to that can be very difficult to scale PINNs to more complex kind of maybe multi-physics or multi-scale problems. And so we talked a lot last lecture about the first one, how do we improve the computational costs of PINNs? Can we speed up how they train, or perhaps whether they can learn across problems so they don't have to be retrained for each solution? And the whole point of these two lectures is to tell you that, yes, these limitations exist, but PINNs by now is a massive research field, and there are so many extensions that try and address these limitations. So what were the ways we discussed to kind of speed up physics-informed neural networks? One of the main ways that I described to you was a very simple idea, and it's just to condition the PINN on additional inputs of the simulation that you're trying to carry out. So I call these condition PINNs. And for example, we looked at simulating seismic waves through the Earth. And if you just trained a standard PINN on this simulation here, you would have to retrain it for every source location that you use. So each new initial condition of the simulation. So what a condition PINN does instead is it adds the source locations, the X and Y location of the source, as an input to the network. And then we train over many possible earthquake source locations when we're training the PINN. And so this trains a surrogate model, which once trained can generalize across the source location, at least in the training distribution that you trained it over. We also talked about these things I call discretized PINNs. And so the fundamental difference with discretized PINNs is instead of using the neural network to directly approximate the solution to the differential equation, and what I mean by that is the neural network represents or directly approximates the function itself. Now instead, we say that the network outputs an estimation of the solution, but only on a grid of points. So we go back to estimating a discretized solution. Now that seems like a limitation, but it has advantages, and the main one is that you can then start to use kind of different neural network architectures, things like convolutional networks that maybe help represent or learn kind of spatial correlations between the inputs and the outputs of the network. So how do we train these networks? Well, we can't get derivatives of the output with respect to coordinates anymore because the coordinates are not input to the network. They're implicit in the kind of output mesh of the network itself. So instead, we use finite differences, taking differences between each mesh points to get our derivatives with respect to x, and t, or whatever the coordinates are. And I also explained to you that we can condition these just like we can condition PINNs on, for example, initial conditions of the PDE. So when we're solving the Burger's equation here, for example, we can add the initial flow velocity, which in this case is a sine wave at time equals t, and maybe even the viscosity parameter of the underlying differential equation as well. And in the same way, this network will train and learn a surrogate model, which will be very fast once it's trained. And here's an example, a paper that implemented these discretized PINNs, and they showed they trained them to solve Darcy flow, so the flow through a porous media. And what I find kind of remarkable or really great about these methods is that they're fully unsupervised. So you don't need any training data to train the surrogate model. All you need to know is what the underlying differential equation it is. It needs to satisfy it, and lots of examples of inputs like initial conditions of the system. And it will learn to simulate just through this learning process and minimizing our PDE residual. So that's the kind of big advantage of these methods. Okay, so I already explained this. We're talking about the limitations of PINNs, and last lecture I covered the computational cost. So this lecture is all about thinking about the other two limitations. So how can we improve the convergence of PINNs to improve the optimizer or navigate the loss landscape better? And then how do we really scale PINNs to problems that we care about, solving like big multi-scale, multi-physics simulations? And these two are very challenging and still definitely open areas of research. So originally I said last lecture, Sid would take over halfway in this lecture. We decided he'll just come and give his first lecture on Friday on the theory behind PINNs. And so that will be the last lecture on PINNs. And then Sid is going to carry on teaching for a large block of lectures, and he'll be talking about operator learning, and there'll be a lot of lectures on that topic. So I'll come back after this lecture here when we start talking about differentiable physics and hybrid workflows, and then I'll take the lectures till the end of the course, as well as our guest lectures. Okay, so let's talk about this second limitation, the poor convergence of physics-informed neural networks. So this is a slide that I showed last lecture when I was giving you the high-level description of these limitations. And let me just tell you what is happening here again. So what I did in this experiment was train a PINN to solve, again, the wave equation. So this is simulating a seismic wave starting at a very point source essentially and exploding outwards. And the PINN after training is able to model the solution, which is good. But what's interesting is if you look at the convergence curve or the L1 test loss as a function of the training step of the network, and what I showed you is that the PINN exhibits this thrashing behavior where only after maybe halfway through training does the PINN actually start to converge to the solution. And if I plot the PINN solution at training step 20,000, so somewhere around here, you can see that the PINN has only learned the initial condition, and it's put zeros essentially everywhere else in the solution. So can anyone remember why this might be the case? Why did we decide this was happening? Yeah, at the back. Yeah. Yeah, exactly. So the underlying wave equation here, a trivial solution is that u equals 0 everywhere. And so this whole part of the domain, from t equals 0.01 to all the way to the end of the domain, is satisfying that PDE residual term in the loss function. Just after the initial condition, the residual loss is probably quite high, but on balance across the whole domain, it's tried to minimize it to probably a local minimum in the loss. So what we have here is a natural competition between trying to satisfy the boundary condition and then trying to satisfy the PDE loss. And it is often the case that there's a trivial solution that is much easier to satisfy in the PDE loss that doesn't satisfy the boundary conditions. And there's this kind of communication that needs to happen between the two loss terms. So this is just reiterating that point. Again, we have our boundary loss in our loss function, and we have our physics loss here. And a key way that we can kind of control the balance between those terms is through these lambda values. So these are kind of, for a standard PIN, these are just scalar positive numbers that we usually choose by hand. So it comes down to human experimentation, like scanning across these parameters to see which PIN converges best. And yeah, if lambda is too small, it doesn't learn a unique solution. And if lambda is too large, then it only satisfies the boundary conditions. So what I've got is many actually different approaches or ideas you can think about to try and overcome these the competition between the lambda terms, or maybe help the network learn through to minimize both those terms at the same time. So the first kind of idea is called hard boundary conditions, or hard initial boundary conditions. So what does this do? This says, well, at the moment, if you look in the loss function, the initial conditions are satisfied in a soft way. That means that the final network that we train might not perfectly satisfy the boundary conditions. The boundary loss might still be greater than 0, for example, and typically that is the case. So, but is there a way that we can reframe the optimization problems or the way that we define the PIN so that the boundary conditions are always exactly satisfied? So we don't even have to worry about matching the boundary conditions in the network. So it turns out there is a way to do this, or there are many ways to do this. And kind of one of the key ideas is to use the neural network as part of a solution ansatz. So do people know what I mean by an ansatz? Some yes and some no. Okay. So what I mean here is that instead of saying that the neural network directly approximates the solution, so neural network approximates U of X and T, what we now say is that the solution or the neural network is part of a mathematical ansatz. So this is just some mathematical function, which is our like guess of what the solution should be. And so the neural network is now part of a mathematical ansatz, and that entire ansatz approximates the solution rather than the neural network directly. And what we do is we design by hand, usually that mathematical ansatz, so that it already satisfies the initial and boundary conditions without us having to train the network. So let's just take this example of the Burger's equation. And we had, importantly, these two initial conditions or boundary conditions. So we said at time equals 0, the starting speed of the fluid should be a sinusoidal curve. And then on the edges of the domain, the flow should be 0. So this is modeling the flow through a pipe. So if we just assume that our solution is approximated by this mathematical function, and the neural network is the only kind of learnable or flexible function, part of that function, what we're doing is we're timesing the network by t minus 1, x plus 1, x minus 1, and then we're subtracting minus sine pi x. So now, just by choosing this ansatz, you can see very easily that it already satisfies these initial and boundary conditions. So you can see that if, for example, I plug in, we want this first condition, u at x equals time equals 0 should be this sine function. So here, when t equals 0, what happens to this whole term here? It's it's 0, right? Yeah, it's obvious. So then u at x equals t equals 0 is exactly sine pi x. So we don't have to use a boundary term here. Same with these two constraints. So if I set x equals to minus 1 here, that zeroes out this term, but also sine at x equals minus 1 is also 0. And so that also satisfies this. So the key point is that and the difficult thing is to choose the ansatz, but if we can do it, then this turns the whole problem from a constrained optimization problem where we have this boundary constraint to an unconstrained optimization problem where all we're doing is minimizing the physics loss, and we get rid of this competition between these two terms. Does that make sense? Has anyone got any questions on that? So where might you not be able to use this kind of handwritten ansatz? Anyone see any limitations with that? Yeah. Yeah.
So
go on.
it's hard to in inequality.
Yeah.
Yeah. Formula.
Yeah. So if your initial conditions have some inequality or something like that. Yeah, maybe. Yeah. So another reason is that here the boundary conditions are very simple. Think about solving a much more complex PDE. For example, I want to model the flow past like an aircraft wing or something, and I have boundary conditions over the wing. Then I have to somehow write that as a mathematical constraint inside of my ansatz. Like, how am I going to determine the distance to the wing so that I can zero out the neural network's value at exactly the wing's location? So there are ways around it, but it can be more challenging when the initial conditions are more complex. Yeah.
Would it be like thousand of a network question between 10 seconds?
Yeah.
Would it be like an approximation for considering neural network find about or
yeah, so actually, if I hear what you're saying correctly, there are approaches where you can like learn distances to the boundary using another neural network, and then use that pre-trained network to help you write these ansatz. So this is another approach. Yeah. Okay, so there's a couple of things to note. A nice kind of machine learning interpretation of this is just to think of this final kind of evaluation of this ansatz. It's just the final layer of the neural network. We're just taking some output of some hidden state, and then we're timesing it by some value and doing a subtraction sign. Like it's a weird kind of activation or kind of layer, but nonetheless, it's just an extra computation on top. And if you think of it that way, then it's really obvious that you can still get gradients of this with respect to the inputs, which we need to evaluate the physics loss, because we can just use autodiff to differentiate through the whole ansatz. And what's also really neat now is we don't need any training data at all. We don't need any examples of the boundary conditions because they're hard constraints. And so the PINN now trains in a fully unsupervised way. And it turns out this can definitely help for a lot of problems. So this is a paper that we're solving the fluid flow. I think this is the incompressible Navier-Stokes equations through a pipe, but the pipe has is constrained in the middle. So it narrows in the middle, and you get a speed up of the flow. So it turns out when they were testing different PINNs, so this is the ground truth solution. When they were testing different standard PINNs, they couldn't find any value of lambda. So when they were using both terms in the loss function to converge onto the solution, probably because there's quite a big competition between the boundary loss and the physics loss. But when they use the hard constraints here, then they were actually able to converge the PINN. So this definitely helped for this particular example. Okay, so let's think about another approach to try and help alleviate the competition between these two terms. And one idea, again, quite a popular idea, is to now think about using adaptive lambdas. So instead of me going and by hand manually trying to scan for the right value of lambda to use, why don't we try to adapt them based on the algorithm or based on the PINN as it's training? So what this paper suggested is that we don't just have a single lambda value for each boundary term. We actually have a single lambda value for every collocation point and every training point that we train the PINN with. So here, when we're summing across all of our boundary points and when we're summing across all of our collocation points, we times each term, each summed element in the loss function by a separate lambda value. So that's the first idea, to have more lambda values, to weight each point by itself. The second idea is to learn these lambda values as we're training the PINN jointly whilst we're learning the theta values, the parameters of the PINN. So how do they learn these? Well, they do this kind of two level kind of optimization, where you first update the weights of the PINN just like normal when you just by differentiating through the loss function. But then you take a step where you update the lambda values, and you do this by doing, instead of gradient descent on the loss function, you do gradient ascent on the loss function. So why does that make sense? Why would you update the lambda values using gradient ascent? Well, just think about dl by d lambda here for the physics loss term. It's very trivial to show that this gradient of the loss with respect to lambda is just the residual value itself. You can just see that because it's lambda times by the residual. So then why does this make sense? Why should we change the lambda value by the residual? Can anyone think of why that's a good idea? Yeah.
We're going to find out where the loss is the highest.
Yeah.
Then go our next normalization step.
Yeah, exactly. You've got it. So what this is doing is saying, okay, where my loss is remaining high, I should increase the value of lambda. I should care more about trying to minimize the residual at that location. So you can think of our residual as a function across the domain, and we're picking out the points where the residual is high, and we're trying to pull them down to 0 and putting more preference on that. So from a machine learning angle, you could kind of think of lambda as like an attention mask. It's like, where should I attend to in my optimization landscape to try and minimize the residual? And so, yeah, this paper implemented these so-called self-adaptive PINNs for the Helmholtz equation and other problems too. And it converges well. This is the PINN solution on this fairly high frequency problem. And what's interesting is you can plot the final lambda values after the PINN's trained, and it's kind of curious or interesting to try and interpret these lambda values. What seems to happen here is the PINN is focusing on the high amplitude regions of the solution, so it's really trying to match these peaks of the waves. Okay. Now, another idea going along this kind of theme of asking, well, where is the PDE residual high in the domain as we're training, and can we target that region? What we can do instead of weighting that region in the loss function, we could actually just add more collocation points where the PDE residual is high. This is another strategy to try and focus attention on the regions where there's error. So you can just imagine. Normally, when we're evaluating the physics loss, we're summing over all collocation points to get a scalar value for the physics residual. But you can just plot this here, which is just the difference before the summation, and that is just a value that you can plot across the whole domain. And so you can just imagine, say we're training a PINN to fit some solution, and it turns out that x equals 0.5, like in the middle of the domain. The residual is really high. What we can then do is say, okay, we're going to sample more collocation points close in the middle, and hope that improves the convergence, because we're really focusing on the PDE residual. So this is the idea, is to adaptively sample these collocation points as we're training by treating this PDE residual as like a probability distribution that we can sample from. So to do it, we just, as we're training, we just evaluate the residual, and we define a distribution that is exactly that residual divided by some normalizing constant to make it a probability distribution. So this kind of, you could think of this as like the PINN analog of adaptive mesh refinement. Like if we have a fixed budget of collocation points, we're like optimizing as we go through where we want to put those collocation points to solve the solution. And indeed, this paper, they tested this adaptive refinement methods. These are the kind of bottom 3 techniques in the table here across different PDEs, so the wave equation, Berg's equation, diffusion, Allen-Gallen. And it does seem that these methods perform much better than kind of just doing grid sampling, for example. The other approaches you could think of, or the other approaches that they used in this table are also interesting to think about. So instead of just using grid sampling, which in general seems to be the worst thing to choose, they also tested random or quasi-random sampling. So these are all the kind of strategies that they tested, and this is what the collocation points look like. I'm not sure, but I think Sid will go into more details about why we should use quasi-random sampling in his lecture. Any questions on this method before I move on? Yeah.
So in practice, with the kind of like a vector of lambdas,
Yeah.
then differentiate and then you differentiate the loss function with respect to these lambdas.
You were talking about the previous technique, so the adaptive lambdas.
Okay, so the same.
Yeah, so
okay.
these are two separate techniques. The first is to adaptively learn lambdas.
Yeah.
The second is to adaptively shift your collocation points.
Yeah.
I'm not sure you could do both at the same time if you're thinking that, because the lambdas depend on where they are in space. But I don't know, that could be an interesting idea. But, yeah. Okay, so we're going to move on to limitation 3, which is scaling to more complex problems. So this is a really important question, really, is most of the kind of applications of PINNs that I've showed you so far are solving what I would describe as toy or simplified problems, where we're solving the fluid flow past a cylinder, or we're doing wave simulation in a very restricted domain. But what we care about really, or what we're shooting towards, is designing new simulation algorithms, new inverse algorithms that can cope with real world problems. Like, can we simulate earthquakes across the whole state of California, or can we do a full global climate simulation? And this is just a very valid question, is, how do PINNs, or more generally, how do these scientific machine learning techniques that we're studying scale to these types of problems? And our traditional algorithms often really struggle in these settings. So, as we add more multi-scale, multi-physics components, as we add higher frequencies, when we start to think about real and sparse and noisy data. And I showed you this example, this experiment last lecture, to describe this limitation. And I'll just recap it. So what we're doing here is we're training a PINN on a very, very simple ODE, which is du by dx is cos omega x, and the solution is just a sine wave. And what we noted is that the PINN converges very quickly for a low frequency solution. But as soon as I increase the frequency of the solution, the standard PINN really starts to struggle. And I had to increase the number of layers and free parameters in the PINN just to be able to model the cycles of the solution, going from 320 parameters to over 60,000 parameters in the PINN. And not only that, the accuracy of the final solution is much poorer in terms of relative loss than the PINN in the low frequency case. So this is a big issue if we want to scale PINNs to these kind of more complex problems. So why is this the case? Like, why is the PINN struggling to solve high frequency problems? So one of the reasons, and it is a big reason, is this kind of so-called spectral bias of neural networks. So hands up who's heard of spectral bias? Okay, maybe one or two, yeah. So this is a general property of neural networks. Even if we're just training a neural network and not a PINN, so just with a supervised loss to match some data. Neural networks tend to prioritize learning lower frequency functions first, or they take much longer to learn higher frequency components in their training data. So this is an example this is a paper that was investigating spectral bias, and what they're doing here is they're just training a neural network to fit a multi-scale function. So this is not a PINN anymore. This is just supervised loss trying to fit this function. And as you see how the neural network trains, it starts to fit these low frequency components of the function first, and then eventually fits the high frequencies. And you can kind of see the frequency content of the solution as a function of a training iteration here. So this is actually one of the reasons why early stopping. Remember, I was talking in the deep learning introduction about early stopping being a good regularization method. It helps to stop your network overfit your data. You know, if maybe this low frequency trend is actually it's a good trend if this data is noisy. This is a reason why early stopping can work. Yep.
In this case, what will be the loss time?
So this is just mean squared error. Yeah, so no regularization. This is just difference between blue line and green line. Yeah. So that's it. So what's really interesting is there's a whole theory behind this that I don't have time to go into, but you can use tools like neural tangent kernel theory to actually analyze under certain assumptions of the network's architecture. You can actually prove convergence rates of different frequency components, and you can show that higher frequencies converge much slower than lower frequencies. So this is great for when we're talking about overfitting or underfitting in machine learning in general. But when we're training these neural networks to solve PDEs, this is not a good situation. We actually want to be able to converge fast on these high frequency components and on the low frequency components, especially if we want to solve these multi-scale simulations. So here's just another example. I showed you when I was describing PINNs, this damped harmonic oscillator problem, and the PINN for the problem that I chose converged very nicely. But what I didn't show you is if I increase the frequency of the oscillator, or equivalently, if I just model the oscillator out to longer time values, the standard PINN actually really starts to struggle, and it takes a long time to fit the solution. And this is related to that spectral bias. There's also some other factors that are making this harder to converge as well. Or just the fact that it's a bigger optimization problem. You know, I need more collocation points to learn higher frequencies so that you know, I'm sampling enough points to sample the frequency well. I need a larger neural network. I need more parameters, as I just showed you in that previous slide, and we have spectral bias. So all of these factors compound and turn the optimization problem into a significantly harder optimization problem. Okay, so we'll just take a short break, and then I'll talk about ways that we can overcome this. And yeah, let's just take a short break. So what I'm going to do now is talk through, again, extensions of PINNs to try and overcome this spectral bias or help them scale to higher frequency solutions. So the first idea is to use something called Fourier features. So what are Fourier features and why they're a good idea? So what Fourier features are, you can think of them as a custom layer inside of our fully connected network. So everything I've been showing so far, we've just been using, for the most part, just standard fully connected MLPs as our network architecture. And we haven't really thought about changing the architecture of the PINN to help it converge. So what Fourier features do is they say, okay, before my fully connected network, what I'm going to do is I'm going to take my input coordinates and I'm going to transform them before I put them into the network. And the specific transformation that I'm going to use is I'm going to use trigonometric transformations. So I'm going to take my x. So x here can contain, you know, x, y, t, however number of dimensions you have as input. And I'm just going to take the cosine of x and the sine of x. Now x is a vector, and I times it by this matrix here, which essentially represents the frequency of those sine and cosine transforms. So this matrix has shape k by d, when d is the number of inputs and k is the number of Fourier features that we're going to use. So So we're essentially just taking lots of sine and cosine transforms with lots of different frequencies, and we're going to form that into just one big hidden state before we put that into the neural network. Typically, we sample these frequencies, this matrix here, just from a normal distribution. So and we fix mu and the standard deviation to sample from whatever frequency range of interest that we want to target. So what does this do intuitively? It's kind of hard to understand, to be honest. What it is doing is putting or transform the inputs into some frequency, to some functions that have a whole range of frequencies before we do kind of a fully connected network on top. So if the fully connected network doesn't learn very much, then we're already kind of our kind of inductive prior here is that the output function would already have lots of frequencies in it. I guess that's kind of the best description that I can give you. What you can do though, and these papers looked into these Fourier features in much more theoretical details. You can actually, again, under certain assumptions of the network, show much more favorable convergence rates of higher frequencies when using, for example, this neural tangent kernel theory to investigate convergence rates. So they showed in this paper here, if I take a multi-scale problem, so this is solving the 1D Poisson's equation, but the solution they engineered the solution so that it has two frequencies in the solution, one low frequency sine wave and a high frequency sine wave riding on top of it. And you know, a PINN without just a standard fully connected network really struggles to fit both of these frequencies. In fact, it doesn't converge at all. And it seems for this case, these Fourier features help and help us converge both on the high and the low frequency components. But it turns out that there's no free lunch here, that you can't just model any possible frequency, and that the frequency range that the PINN likes to converge on when it has these Fourier features very strongly depends on these mu and standard deviation of the Fourier features of the input to the network. So the problem then becomes trying to figure out which frequencies to include in your Fourier features to best match the solution that you want to try and solve. Does this make sense, or any questions on this? Yeah.
Question in general for all these PINN adaptations.
Yeah.
I actually need to know how the solution looks like in order to apply all of this, right?
Yeah. Yeah, and so and you're right, you actually pointed out the main limitation of these extensions and also the ones that are coming up, by the way. And I don't know of a good way to get around this. I would argue that traditional numerical methods also have this problem. Like if you're doing FEM, we have to design, we design the mesh so that it fits the solution that we think is going to occur. And the traditional method to solve that is to use like adaptive meshes, and I guess those adaptive lambdas or adaptive collocation points is like the PINN analog of that. So I think what you'd have to do in practice is combine many of these extensions together, and that is what kind of a lot of these latest papers do, is they're using lots of extensions at the same time. Any more questions? Okay. So here's another approach to try and overcome the kind of spectral bias or challenge of scaling PINNs to large problems. And that's to combine PINNs with domain decomposition. So what's the overall idea here? Well, the idea is to say, okay, that global optimization problem, trying to fit one neural network across all of the collocation points, is a really hard and complex problem. What if we take a divide and conquer approach where we try and turn that big global optimization problem into lots of smaller, perhaps coupled optimization problems? And just the hypothesis here is that if we take a divide and conquer approach, then those coupled optimization problems are easier to solve than the single global optimization problem. So what is the exact divide and conquer approach that we would use? Well, this idea is to divide the modeling domain, so the whole solution domain, into many different subdomains. And then instead of having a one single network that represents the solution everywhere, we place a separate neural network in each subdomain of the solution. So for example, here we would have a neural network that learns the solution in this red region, another one in the yellow, and another one in the green region. Okay, so kind of one of the first papers that proposed this idea was extended PINNs. So they did exactly this. They said, okay, here's my solution domain. I'm going to have 3 neural networks here, and each is going to tell me the solution. Each is going to take the coordinate as input and give me the solution as output, but it's only going to model it in that subdomain and not the whole solution. So then the question is, how do you train each of these networks, and what loss function do you use to train each of them? And so here is the loss function for an individual subdomain. So M here is the number of the subdomain. And actually, the loss function looks very similar to the standard PINN. We have the boundary loss, we have the physics loss, but the important thing that we have to also include is interface conditions. So we have to say the solution along the interface should match across these different subdomains. And that's the really important extra term that ensures communication between the solutions and makes sure that the solution globally as a whole obeys the kind of global boundary conditions and connects properly. So, I mean, this is a general property of any domain decomposition method for solving differential equations. Is they inherently have to have some communication between the subdomains to be able to solve the global problem. And this is where it turns up in these extended PINNs. The big kind of issue with this is that this interface condition, making sure that the solution matches across the interfaces, is not a hard constraint. It's just softly constrained in this loss function and is often not minimized fully. And you can really tell this when you look at the difference between the true solution here and the predicted solution after we've trained all of these subdomain networks. And what we have is discrete jumps in the solution. And so this doesn't work if we expect the solution, or is maybe not a good representation if we expect the solution to be continuous everywhere, for example. On the flip side, for some problems where you do actually expect a discontinuity in the solution, or maybe you have kind of multi-physics or different regimes in the solution, sometimes this idea of having a separate neural network does help you model these discontinuities in the solution. So there are some cases where this works. Yeah, I just described this limitation. So I'm going to describe now a different approach, which is the same idea. So we're using domain decomposition and having a separate neural network in each subdomain when we're training the PINN. But the difference here is that we're not going to have we don't want to have these discrete jumps in the solution of the interfaces. And so this is some work that we did. So we proposed finite basis physics informed neural networks. And so how are they different to these extended PINNs? So as I said, FB PINNs, they do the same thing. So they divide your so now this is a 1D problem to make it easier to understand. They divide your solution domain into lots of subdomains. But the key difference is that we now say that these subdomains are overlapping rather than non-overlapping. So you can see each subdomain here has some overlap region here. And what we say is we have a neural network in each subdomain, and we say that the final solution now is just simply a summation, a mathematical summation of each of the neural networks times by some window function that constrains the neural network to that subdomain only. So these window functions look like this, and when we times the network output by this window function, we're basically saying the network's output outside of its subdomain is going to be 0 because that's forced by the window function. So this is a very different way to kind of frame the problem, and what we're doing now is we're explicitly putting in the domain decomposition in an ansatz of the solution. So we're mathematically kind of writing in the domain decomposition by way of summing and applying these window functions. So if we train this FP pin, and I'm going to say how we train it in a minute, but we train it on this sinusoidal function, and you look at the outputs of each of the subdomain networks times by their window functions, you can see what the solution that each subdomain network is learning. And in the overlap region, they're being summed together, and the summation is the full solution. So the difference between this and the XP pin approach is that by mathematical construction, just by saying that the solution is this ansatz with the summation times by these window functions, this solution is continuous everywhere. There's no discrete jumps in the solution, because this whole thing is a smooth mathematical function, as long as we choose smooth and continuously differentiable window functions. And therefore, we can just train this using the same loss function as pins. We don't need to have these extra interface conditions in the loss function anymore. We can just use the standard pin loss function to train all these subdomains. And in that way, you can just think of this ansatz here as just a custom neural network architecture. That's all it is you could think of each subdomain as like a small neural network, and they're all summed together to get the final global solution. And that's just, that whole thing is just some custom architecture that we're using. Any questions on how we've framed the problem and framed the domain decomposition as an ansatz of the solution? Yeah.
Is there a way to divide
Yeah, so you're getting back to the point asked earlier about how do we choose the domain decomposition? Yeah, and so again, this is the limitation of this method, and domain decomposition in general is you typically want to choose the decomposition so that it fits the solution. So the standard FE pin approach doesn't do this. You have to know something about the solution a priori, but you can choose the domain decomposition to fit it if you do. So we're not limited to having like fixed size subdomains here. You can see each of these are actually different sizes. And what's cool and interesting, and we're actually researching at the moment, is whether we can learn these window functions. So whether we can actually learn the subdomain decomposition, and we basically parameterize this window function. So for example, we say that the mean of the window and maybe the width of the window are learnable parameters, and we learn them inside the pin loss. So here's an example of the FE pin training on this damped harmonic oscillator problem. And the FE pin works much better than the pin in this case. And one of the tricks that I didn't tell you about is, before we pass our coordinates into the subdomain networks, we actually normalize them between -1 and 1 within the subdomain region itself. And so what that does, if you think about modeling a very high frequency function, if we just have a subdomain to learn one cycle with that function, when we normalize in the subdomain, we're basically stretching out that function into a low frequency function from the network's point of view. So this is a way to get around the spectral bias by normalizing the inputs to stretch out the frequency components. And this is another reason why they're training fast, and using that normalization is really important. What's your question?
I look at these ways, sort of how I would do it in a finite element setting, that I want to look at it as some basis function.
Yeah.
I want to minimize all those.
Yeah.
basis functions.
Yeah, this is why we called it finite basis pins, because the inspiration was from finite element methods, where we say our solution, it's very similar to this, is where we say our solution is the summation over lots of local basis functions. And that's exactly how you interpret this. You say, my neural network is now learning that basis function, rather than the basis function being like typically a polynomial or a tent function or whatever you want to choose. So I really like that interpretation, because then you're starting to really have a unified understanding of like FEM and how FEM relates to pins, for example. Pins, like a standard pin is like FEM with one element and a really big basis function. That's the way to think of it. And that's also interesting to think about the computational speed, because FEMs can be solved much quicker than PINNs because they use very simple basis functions. If we have a polynomial, then we don't have to use gradient descent to get the parameters of that polynomial that we're fitting in FEM. We just use a linear solve. Whereas here, because we have a nonlinear basis function, we're relying on gradient descent, like optimization algorithms to get those, to fit those basis functions. So you can start to see the playoffs here. Maybe this thing here is more expressive and the FEM is less expressive, perhaps. Like, yeah, and depends what your solution is that you want to model. The other cool thing, apart from the fact that it converges much better than the PINN, is that it takes much less flops to train. So this is the, you know, raw flops that it took to train the FE PINN. So can anyone tell me, based on this slide, why not only does the FE PINN is more accurate, but it takes many less flops? Based on the numbers that I'm showing in this slide. Yeah. The subdomain is much smaller. So the question, I'm not asking about whether it's easy to train. I'm asking why it's is less expensive to train. So why do we need less flops here? So I haven't actually made this clear. So these lines here have the same number of training steps. So we use like I don't know however many 15,000 steps for each thing here. But after 15,000 steps, we've only spent like 0.2 flops to train the FE PINN versus four flops to train the PINN. So why did it take less flops? Yes.
What's a flop?
Floating point operation. So this is a measure of how much number crunching did we do to train the PINN. So how many operations? Yeah.
Is the architecture the same for both? So the number of ways.
So the architecture is not. So the PINN is 2 hidden layers and 64 hidden units. The FE PINN has 15 subdomains, so 15 subdomain networks, but each subdomain is much smaller. So it's 1 hidden layer and 32 hidden units. So I think you've basically got the answer. With FE PINNs, we can get away with using much smaller subdomain size, network sizes in each subdomain, because they have to learn a much simpler function. And that basically means that there's a lot less computational flops required to train all those subdomains. It's actually computationally training the FE PINN is equivalent to training a single global network with the same number of weights as each subdomain network has. So that's another kind of cool property of FE PINNs. So we can extend to multiple dimensions very simply by doing a domain decomposition over high dimensional spaces. So this is what it would look like in 2D, very analogously. We don't change the ansatz or the way that we sum the solution at all. So here's an example of doing FE PINNs in 3D or 2D plus time. And what the simulation we're trying to do here is a multi-scale wave equation simulation. So we're starting with 3 different sources now, and each source has a different frequency range. So this simulation would be very challenging to converge a PINN on, and whereas the FE PINN here does converge fairly stably as it trains. And the code that we have now is fairly scalable. So it's actually running 30 by 30 by 30 subdomains, so 27,000 neural networks at the same time we're training. But only takes 2 hours. This is still slow compared to FEM, but definitely faster than training a global PINN. And about 1 million parameters and very small subdomain network sizes in each subdomain. So 1 hidden layer, 8 hidden units. If you think about the basis functions we use for FEM, we're kind of approaching those now. One last slide on FE PINNs. Another cool thing is that just by using the domain decomposition, you can actually start doing parallel computation. So you can train them in a very highly parallel way. So one idea of implementing this, for example, on multiple GPUs, is you would push each subdomain to a separate GPU and feed all of its individual points separately to each GPU. And you would compute all of the outputs of the subdomains in parallel then you would need this one communication step where they share their outputs in the overlapping regions. And then we show in our paper that you can then backpropagate and train the networks in parallel without having to do any more computation. So long story short, they're very parallelizable as well. And so this is another key kind of consideration is, if I want to scale to a bigger problem, can I put it on multiple GPUs or multi-threaded cores, for example? Okay, so I've covered all those big limitations, the computational costs, the poor convergence, and the scaling to more complex problems. What I haven't covered is all of the other PIN extensions, and like I showed you before, there are now hundreds of PIN extensions out there, and it's a really big research field. And this slide is just trying to cover some of the big ideas that I've missed or I haven't had time to cover. And so there are many more extensions. So there are extensions, for example, in the differential equations or the classes of differential equations that you can solve with PINs. I've just been talking about fairly simple partial differential equations or ODEs, but you can solve much more exotic equations like fractional equations or stochastic PDEs, for example. We've only been using the strong form of the underlying differential equations in our loss function, but you can also use other forms like the variational form, and this starts to, again, make PINs look more like finite element methods. You can use mixed formulations, and many other approaches. Another thing to do is to incorporate uncertainty estimation when you're training the PINs. So can you actually learn, for example, when we're doing inverse problems with PINs, can we learn the distribution of possible parameters given the observations that we have when we're trying to solve an inverse problem, rather than just guess a single point value of what that parameter is? So there are Bayesian PINs, there's GAN PINs, etc. There's a lot of innovation on the architectures. So, for example, using adaptive activation functions, using these Fourier features, using sign activation functions, using wavelet layers, using LSTMs. I don't have time to go into the pros and cons of all of these, but there's a lot. And then there's also been a lot of work on the optimization side, and instead of just using a standard maybe Adam optimizer that we use for most of other machine learning tasks, are there more bespoke optimizers that are more suitable for PINs? And some of these look into NTK theory to kind of understand, to design the optimizer, and you can do causal training strategies, and there's many other approaches. Also, by now, there's a huge ecosystem in terms of the software libraries of PINs now. So NVIDIA have this platform called Modulus, which it allows you to write and train a PIN very quickly. Also incorporates many other SciML algorithms as well. There's DeepX DE, there's neurodifferential equations, there's PINNs, there's many other libraries as well. So in the last, I have two more examples that I'm going to show you in this lecture. The first is doing Bayesian PINs, so trying to incorporate uncertainty estimation into the PIN. And then the final one is to look at wavelet layers as a different type of architecture to use. But if you're interested in this, I recommend this review paper or yeah, just reading around. There's lots of great material on PINs out there. Okay, so let's talk about Bayesian PINs, and this is a technique proposed by this paper. So what we want to do is we want to frame this problem of solving the differential equation as a probabilistic task rather than just learning a single solution. So what do I mean by that? The task that they imagine in this paper is to say, let's have, instead of exact measurements of the solution and the boundary values and maybe the forcing function in the PDE. So this is the terms are different here, but it's the same setup. So this N here describes the differential equation, the operator. And we just apply the differential equation operator to the solution and get some forcing function as the differential equation. And then B here determines the boundary operator, and we get some boundary value here. So this is just a different way to phrase the problem. So given noisy values of F and B, so this is values of our boundary and values of this forcing function in the differential equation. and maybe some noisy values of the solution itself. Can we fit a neural network to model the solution? But not just a neural network, can we fit a Bayesian neural network to the solution? So how is a Bayesian neural network different? The difference is that instead of having single values for the weights, we assume that the weights are actually drawn from some prior distribution. Typically, we assume that they're drawn from a Gaussian distribution. And the goal of the learning problem now is to say, given all of these noisy data points, can I infer what the posterior distribution of the weights is? So can I actually, learn or estimate the probability of theta given the data? And we don't just want to get a single value of theta, we actually want to get this whole distribution. Or if we can't get the distribution, we want to sample from this distribution. So we want many possible samples of theta given the data. So that's kind of the probabilistic setup of it. And you have to make some assumptions on the posterior, or actually on the likelihood here, which is the probability of the data given theta, and on the prior, which is the probability of the weights, so that you can sample from this thing. And the assumptions that they make is that the data likelihood, this is the probability of observing the data, is just we just assume that these data points are drawn from some Gaussian distribution, where our neural network models the mean of that distribution. And then we assume the priors on the weights are just Gaussian priors, as I was describing here. So I appreciate that that's quite heavy in terms of the theory and the model, and I'm not going to go into it in detail, but I'm trying to just give you a high-level perspective on the goal of this model. So then the question is, once you've got this model and this model, how do you estimate the posterior? And one way to do it, and they show in the paper that you can actually use standard ways of sampling from the posterior. So for example, Hamiltonian Monte Carlo, or more generally Markov chain Monte Carlo methods to sample from this distribution. And so what they did in the paper is they showed this example of using a Bayesian PINN to solve the 1D Poisson equation. So this is the underlying differential equation. And we're just going to assume that the training data that we have now are some noisy values of the boundary values. So these are the boundary conditions here that on the edges of the domain, the solution should equal these edge values. These are the noisy BI values here. And then we also have some noisy values of F here. So these are noisy values of this forcing function. And you can see that we have however many, 10 or so points. And these are essentially our collocation points when we're training the PINN. So when you fit this Bayesian PINN, the advantage of doing it now is that you get this whole posterior distribution, and you can sample many possible solutions from that posterior distribution. And so what you're seeing here is the best guess or the mean guess of what the solution is from that posterior distribution, and also what the mean guess of the forcing function is. So I think this is quite a nice way of encapsulating or modeling the uncertainty in our training data, because we're not giving the PINN the full value of F, we're only giving it a finite number of samples of F. It's quite cool that this method can kind of estimate the uncertainty on F given that finiteness of that training data, and then also give you the uncertainty on the solution at the same time. So in this paper, they extend this to doing inverse problems with PINNs as well, and it turns out you can also get a distribution of possible underlying parameters by training this Bayesian PINN instead of just a single estimate of what the underlying parameter is. I highly recommend you have a read of this paper to understand it in more detail if you're interested. The difference between the first column and the second column here is the second column just has more noise on these observations, and you can see that as we add more noise, the Bayesian PINN does give more uncertain estimates of what the solution is, which is good to see. Okay, one more example, and then we'll finish a little early. Is on these custom neural network architectures for PINNs. And so what I'm going to describe is some of the results from actually one of the master's students in our lab. And so Davide Starb here was a previous student of the deep learning and scientific computing lectures. So this is an example of one of the master's students that we supervised. And what he was really interested in was modeling the elastic wave equation with PINNs. So all the examples of the wave equation I've been showing before are the acoustic wave equation. Elastic wave equation is modeling both longitudinal and transverse waves. So it's a more complex version of the wave equation. And the solution in this case, you model the displacement in the X and the Y direction. So the solution is actually a vector field rather than a single scalar value. So what we've got set up here is a elastic wave propagating through a constant or homogeneous medium, and you can just see it propagates outwards in a circular pattern. And so the observation that we tried to do here was to say, okay, well, we know something about the solution here, like this. Well, we were trying to think, how can we characterize the solution? How can we write into the network architecture that the solution should be wavy in the kind of loose sense? And the idea was to say, well, maybe we can represent the solution as a summation over many wavelets. So what is a wavelet? This is an example. It's like a localized pulse. And there are many different wavelet functions, but this is known as the Ricker wavelet, this one that I'm plotting here. And you can kind of see that you could think of the solution as the summation of these wavelets where these wavelets are like slowly propagating outwards and their amplitudes are slowly changing over time, for example. And maybe as they go through different velocity regions, the width of the wavelet like stretches out or stretches in. So and somehow it makes sense to model this as like a summation over these. So you could also think of this as a physics-informed kind of basis that we're learning the solution. So we're kind of, instead of just learning the full solution, we might just want to learn the amplitude of these waves and the amplitude of these wavelets and the width of these wavelets, for example. So what he did was propose this architecture, which he called an encoder-decoder PINN, where what we did is we had, at the start, we took the coordinates and we passed them through some fully connected network here. But instead of saying the output of that fully connected network was the solution, we said, actually, that fully connected network, that encoder part, is predicting the parameters of these wavelets. So we set up the problem with, say, 100 wavelets or 200 wavelets or more. And the job of this network was just to predict for each of those wavelets what is the location and the width and the frequency of those wavelets. So then we evaluate those wavelets given those parameters. We need the input coordinates to evaluate the values of those wavelets for those coordinates. And we sum them together to get our ansatz. Now he tried training PINNs just with this encoder and summation kind of part, and found that the convergence wasn't as good. And this was perhaps too strong of a constraint just to say that the solution is just a pure summation of these wavelets. And the best model that he found was actually to add an extra fully connected network afterwards to learn to sum these wavelets in maybe a non-linear way, or maybe just do a non-linear combination. So what we're doing is we're trying to add some physics constraints into the network, but still keep it flexible to learn like the solution around it. And here's an example simulation of on the right here is just a standard fully connected network, PINN training on the elastic wave equation. And then on the left is his proposed model, this encoder-decoder wavelet architecture. And we're running this architecture with 128 wavelets and some small encoder-decoder fully connected networks either side of it. And he got some. This is just one result from his thesis, but he got some over many different tests. It turned out that this architecture was fairly convincingly better than the PINN for different elastic wave equation simulations. And you can see it in this example. So if you look at the difference plot here, this is the difference between the finite difference modeling and the PINN solution. And the error here stays very low for the encoder-decoder PINN, but for the PINN, it grows much quicker. So we get to something like 10% error here, whereas it's maybe 3% here. So just another example of changing the network architecture to fit the type of solution that we want to model. So we're finished discussing the limitations and extensions of PINNs. just to summarize, standard PINs for sure have some big limitations. Their computational cost, their convergence, their poor scaling. But the good side is that there is a lot of extensions and a lot of possible ways to overcome those limitations, depending on the problem that you have. And this is very much still an active field of research, and it's very exciting to see this field develop. So yeah, I hope you enjoyed learning about PINs, and well, you'll have one more lecture about the theoretical aspects on Friday. So yeah, thank you.